Alrighty, so muzzle velocity is what this video is about. What is muzzle velocity? Muzzle velocity is the velocity or deployment, if you want to call it like that. Most of you guys are going to deploy forcibly. You're going to be pushed out of the vehicle that you're on. And that's what we're going to discuss today is how are you going to be pushed out? What is your velocity as you leave the vehicle, okay? And how you can calculate that, okay? So that's what we want to talk about today. There's a page in the book about this, of course, and it is called Engineering Analysis, Muzzle Velocity. There's a great picture that I drew. It's awesome, okay? And so I'm going to redraw this page. You can follow along with the page. So one of the most important things about muzzle velocity is realizing what your assumptions are, okay? Very important, almost as important, or probably as important as the problem itself, realizing what your assumptions are. So I'm going to draw a two-dimensional muzzle. It's kind of short. So this is our muzzle, all right? We're going to have our projectile is going to be in our muzzle. Just going to draw, basically, I'm assuming this is a tube and our projectile is a sphere. It's supposed to meet down there. Just ignore that. And so our projectile is going to have a little m, little mass, little m. We're going to have a distance that we can shoot down, little d. That's the distance that we go. Pop quiz. What is the maximum distance that your barrel can be? What's the maximum distance? That's right, 44 centimeters is the total length your barrel can be. Most times I say that D is 40 centimeters or 0.4 meters because it's a nice round number for starters. Also, the paper box that you're in, the maximum length is 44 centimeters. And so it's very unlikely that you're going to be that you can push it the entire length. So that's why I said 44 or 40 centimeters. You could do some weird angles across the box if you wanted to get more distance out of it. But if you just if you just do the straight lengths and stuff, 44 is the maximum dimension of that box. And so about 40 centimeters is about how long you can, is about how long you can propel your payload out. So your probe. Okay, so just to give you an example, what is muzzle velocity? This is what you're going to do. Ready? Okay, that's what you're going to do. So this is your barrel. My little foam thing here is your probe that you're going to shoot out. And most of you guys, so here's our little probe that we shot out. Most of you guys are going to use pressure. You're going to use not air pressure like I used with my lungs, but you're going to use helium, high pressure helium, because there's high pressure helium on board the spacecrafts. On board all spacecraft, typically they have high pressure helium that you guys have access to. And once again, just because it's fun, okay, that is what we're doing. Okay, it's a t-shirt cannon, it's a potato gun, whatever you want to, whatever you're doing. We're going to be using pressure to take something that was at rest and push it down and so that it leaves with a velocity. Okay, so we have our mass. It's going to exit with a velocity final. What's our initial velocity of this guy? We have initial velocity, the initial equals 0, right? It's not moving. The spacecraft is moving, but with respect to the barrel, this probe inside the barrel itself is not moving at all, okay? So, what else do we got? Get my cheat sheet here, sorry. So, let's look at the equation. I don't know if you guys have had this in physics yet, but there's a basic physics equation that covers this, and it's V final squared equals V initial squared plus 2AD. Okay, this is our exit plane there. Okay, and our barrel it's round, right? Our barrel is like this. It's round. So I'm drawing it like this. I'm drawing it two-dimensionally, but it's round. It's got a cross section to it. That's what a cross section is this circle here is the cross section of this tube. Okay, so this is the equation that defines what we're looking at. Okay, and so V final is what we're looking for. That's our unknown, right? V initial, like I just said, it's 0. 2 is 2. D is the distance we're going to travel. What is A? A is acceleration, okay? So our probe is going from 0 to some velocity, so we know it's accelerating, right? What is something else? So if something is accelerating, if a mass is accelerating, what do we know about that mass? There's a force pushing on it, right? We know that one of Newton's laws, I can't remember which one, F equals ma. Force equals mass times acceleration, right? Y'all have heard of this before, maybe, hopefully, some of you? Okay. So F equals ma. Whenever you have a mass that's accelerating, there's a force acting on it, okay? And in our case, what was the force? What was my force? High pressure, right? Pressure from, in this case, air, but you're going to use helium. So high pressure, let's just call it gas even. High pressure gas. So there's a pressure. Do any of y'all know what a pressure is? When you fill up your car tires, what are the units? Pounds per square inch, PSI, right? You know, like I need 25 PSI, whatever. Pounds per square inch. So a pound is a force per square inch is over an area. So a pressure is a force over an area, a big A, okay? And an area, in our case, area is the area of the tube, the area of this circle that the tube makes, okay, the cross-sectional area. So that's what I'm going to draw right here. That's our area, A. I'm trying to draw it three-dimensionally, but y'all, you get what I'm doing here. I'm not an artist, okay? So this force, I don't want to draw a negative. That makes it confusing. This force and this force are the same force, okay? Because this pressure is causing the force that's moving the mass, that's accelerating the mass, right? So let's just set these equal to each other. So, so if we rewrite this, we have F equals PA, right? Rewriting this equation. So we have MA equals PA, right? So MA equals PA because the force is the force. All right. So if you square this, you have mama equals papa, but it doesn't help us at all. It's just a stupid joke. I like it. It's funny though. You laughed. I mean, you know you laughed. Just admit it. Own up to it. Okay. So, however, let's solve for acceleration. That's what we're looking for. We don't know what our acceleration is. We don't know how to calculate acceleration. We need acceleration. So we solve for acceleration. A is big P, big A over mass. So acceleration is the pressure times the cross-sectional area divided by the mass of the thing that's being, of the probe. Got it? So let's rewrite this equation. Let's put it over here. Woo! Okay, so V final squared equals V initial squared, which we said is 0, plus 2 times A, which is PA, it's a weird A, PA over M times D, times the distance that it can travel. Okay? So we end up with, let's just make this a little simpler looking, V final squared equals 2 PA over M times D, okay? So, that's to solve for final velocity. What if you know your final velocity and you want to solve for the pressure, like we did in the examples in the introduction, right? They wanted to solve for the pressure, okay? Then you just, algebra, that's all it is to it. It's just algebra. So let's see that, I've not practiced this, let's do this on the fly. So you'll have, pressure equals, so take the 2 on the bottom, the D on the bottom, V final squared times M, the A's on the bottom, A, the 2, and the D. Is that right? So if you want to solve for pressure, you just algebraically manipulate it. I know pressure is V final squared times the mass divided by the area divided by 2 divided by the distance it travels. And you can do this for whatever you're looking for. Most teams are going to look for final velocity, or they'll solve for pressure that they need to, they know the final velocity that they want, and they solve for the pressure that gives them that final velocity, okay? So, I said at the very beginning that the assumptions are the most important thing in this. What have we assumed so far? We've made a lot of assumptions, we just don't know it, okay? The first thing, and you can cheat if you look in the book, which I will too. The first thing, this value for pressure, right? Okay, if I'm blowing my projectile down this tube, if I started right here, I started at the very end, if I started right here, oh, did it work? Oh, it's, Okay, it's very difficult to do, to get the entire distance down. Oh, that's gross. Okay, so what happens as this mass moves down, okay? The pressure is going to do what? It's going to drop because this mass is going to make, this air is going to get more and more, so the pressure, this pressure is going to drop, okay? If you start with just a given pressure, it's going to drop. So does this pressure drop as the mass is moving? Does this pressure decrease at all? No, it does not. It's a constant pressure, okay? So our assumptions, number one is that we have a constant pressure. Constant pressure. Is it true? No. Is it close? It's pretty close. The pressure difference from here to here is going to be very little, especially if you use a lot of pressure. The pressure won't change that much. Otherwise, also, you can't solve the problem. It becomes like a really bad calculus problem. No one wants to do that. So constant pressure is our first assumption. It's an assumption. It's good to make sure that you state that when you talk about this problem with somebody. That we assume that the pressure, as the mass goes down the tube, the pressure remains constant, which is not true, but it's not a bad assumption. Number two, what would happen if the pressure, what would really happen in this case is that the velocity at the end would not be quite as fast, right? Because the pressure would drop a little bit, and as the pressure drops, here's your velocity final. As the pressure falls, your velocity is going to fall a little bit, right? So what's going to end up being is that your velocity won't be as much as you thought it would be, by a little bit. That's all that's going to be, okay? So the second one, I'm going to go in order from the book. The second one, this probe, this mass, actually touches the walls of our tube, of our barrel, right? It touches the inside walls of the barrel. Whoops. What's going to happen right there? We're going to have friction, right? But do we have a friction term in here at all? We do not. So we assume no friction. No friction. Is that a good assumption? It's iffy. It depends on what the materials are made of. And again, with a high pressure and a short barrel like you're going to have, it's not that bad of an assumption. And again, if it becomes a very, very difficult problem to solve if we assume if we have to integrate friction in there, because friction is going to change as you go down the tube. Again, no friction is what we assumed. However, we also assume this is one that people kind of miss a lot of the times, is that we assume it's called perfect fit. Is that in a normal situation, especially with no friction, gas would come around the edges of the probe and get in front of the probe. It would circle in front of the probe. Like if you ever see a bullet leave a barrel, slow motion photography of a bullet leaving a gun, there's always fire in front of the bullet, right? Because some of the gas got around the bullet. Bullets use high pressure gas. Some of the gas got around the bullet. And so the bullet so there's fire and the bullet leaves, right? So that's what's going to happen. And what that does is, first of all, you lose pressure. So that's one thing that it causes, is you lose pressure. It also puts pressure in front of a pressure in front of this mass that opposes the direction of the mass. Okay, it's a pressure that pushes in the other way because it's a pressure. And sorry, my phone's ringing. I didn't know what that sound was. So what that does is it would cause, it's called a back pressure is what it's called. But we assume a perfect fit. So we assume that there's no back pressure, perfect fit. All of our gas is used to push our probe in one direction. So we assume that none of the gas gets around the probe. So this is not there. We assume this does not happen. Okay, that's an okay assumption. Again, it's an okay assumption. Again, what would happen with the first one? The velocity would be a little bit lower. The second one, the velocity would be a little bit lower. The third one, the velocity would be a little bit lower because you'd have a back pressure. The second one, you'd have friction. So in the last one, the fourth one, there's no gravity in this at all. There's no other forces besides the pressure, really. There would be gravity, depending on the way I have it drawn, gravity would be pulling this way. That's the direction of gravity typically, is down. We just don't know where gravity is going to be, we don't know where gravity is in our case. So that's why we ignored it. And for the most part, the pressure is going to be so much greater than any gravity that this probe will feel. We're not going to worry about it too much, okay? So we're going to neglect gravity. So, and again, that would probably cause you to be a little bit slower. So all four of these assumptions would basically end up with your velocity being a little bit slower at the end than you calculated it would be. So that's all that it amounts to. So again, it's important to know your assumptions, and it's important to know what those assumptions, how those assumptions impact the problem. So you can explain that, yeah, we have four main assumptions in this problem, and basically what those assumptions amount to is that the velocity we calculate is going to be a little bit above the real velocity. But are we 80 to 90% correct? Yeah, we are. So I don't think there's an issue. So we're going to do an example here, because what you guys want to do, this is some good calculations here. Lots of different variables to play with. Okay, there's a distance here. There's a area. There's masses. There's pressures. There's lots of different things. Lots of different variables you can play with. So we're going to give you guys an example, so you can set up a spreadsheet, and then you can check your spreadsheet against our example, and then your spreadsheet is set up properly. You can keep going. You can keep calculating with your values. Does that make sense? Again, so that's why we give examples, is so that we can calculate, so that you guys can calculate with your values. So here's my example. I'm going to get my cheat sheet up here. So I've got in this one I'm going to have a diameter. I'm going to define a diameter, because that's how most of you guys are going to define your. You guys won't define an area. You'll define a diameter of your barrel, right? So I've got a pressure. My pressure, I'm going to say a pressure is 1,000 psi, pounds per square inch. I'm going to say the mass of my probe is 0.25, a quarter kilogram. Okay. The distance, this distance that the probe is going to accelerate, like I said, is going to be 40 centimeters. And then the diameter of the barrel is going to be 5 centimeters. 5 centimeters, okay? So now I've got units all over the place, right? I've got kilograms, centimeters, and PSI, pounds per square inch. So when you do calculations, always use basic, first of all, never use English units. I think in PSI, I think in pounds. I can relate to pounds, but I never do calculations in those. Oh my goodness, holy cow, that's terrible. So change your PSI. You can put it in Google. 1,000 PSI equals question mark. The pressure, the value, or the unit for pressure in the metric system, or SI units, is the Pascal, big P, little a. So you can put 1,000 PSI equals question mark, big P, little a. Google will tell you. Google's awesome that way. So, but the answer for 1,000 PSI is going to be 6 million. There's lots of Pascals. 6,894,800 Pascals. Okay, that's the unit. That's the conversion there. The mass is going to stay as kilograms. Check. Remember, we want to use meters. So this is going to change to 0.4 meters. The distance that we're traveling, this little d, big D is. We don't need big D, we need area, don't we? So the area is going to be, in square meters, is going to be 0.002 square meters, okay? So that's what we got from all this. So our equation again is V final squared equals V initial squared plus 2 times PA over times the distance. Again, it's at rest, so V initial 0, so V final equals, V final squared equals, let's just say squared equals 2 times 6,894,800 times area, which is 0.002 divided by the mass, which is 0.25, times the distance, which is 0.4, and that equals, so we take that, then take a square root, so V final. Don't forget this is squared, so once you get this and you square root it, you get the final velocity, which is 208 meters per second. That's pretty quick. That's, what is that, 208 meters. So 100 meters is a football field with one end zone. So that's 2 football fields and 2 end zones, not all 4 end zones. And plus 8 more meters is probably another couple end zones. So that's almost 2 complete football fields with end zones in 1 second. That's pretty quick. So what you want to do is you want to go back and check, okay, how much is this going to rip us apart if we go from 0 to 208 meters per second in 0.4 meters? And I mean, what is that? Like this far? If we go from boom to whoosh, you know, how much is that going to jerk our head back? Is that going to rip our components apart? Is that too much velocity? So you can check, you know, how do you check for acceleration? How do you check for that? You say, this is just making this up off the fly, V final equals, the same one actually, V final squared equals V initial squared plus 2AD, okay? So you can just solve for A right here. Here's your acceleration right there. That term right there is your acceleration. So find out what that is. That's going to be in meters per second squared. That term will be. And then you can compare that to you know, the accelerations that your probe can tolerate. If the term G is, if you just take that acceleration and divide it by 9.81 or divide it by 10 is close enough, that gives you how many G's it feels if your probe is listed in that it can tolerate so many G's. A G is just a 1 Earth gravity basically. So you just divide it by that. So, but here's your acceleration term if you want to figure out how fast your probe is accelerating. Pretty quick, by the way, so just check that out. So that was muzzle velocity. Everyone is going to deploy from their vehicle. Some of you guys are going to be deployed like shoo, fast out or whatever. Some of you can just be deployed very quickly, mildly out. You know, you don't have to go that fast. But some of you, again, some of you might know your exit velocity. You might want to solve for pressure. You just manipulate that and you're good to go. So that's it for muzzle velocity video. If you have any questions, contact me or PJ or your UAH PM. Thanks a lot. Bye.